Welcome back to the Deep Dive. It is Wednesday, February 18th, 2026, and I want you to start by picturing a scenario with me.
Okay, I'm listening.
Imagine you have hired the world's greatest detective. We're talking, a true Sherlock Holmes-level intellect. This person can deduce the chemical composition of cigar ash just by looking at it. They can simulate these incredibly complex criminal scenarios entirely in their head. They are a reasoning genius.
Okay, I'm picturing it. Sounds like an expensive hire.
Very expensive. But here's the catch. You hire this genius,
Yeah.
you put them in a room to solve a crime, but you blindfold them.
Ah.
And you, the person who knows nothing about solving crimes, you are the one who decides which 3 pieces of evidence to hand them. So you hand them a receipt, a button, and a blurry photo, and you say, solve it.
That's a recipe for disaster. The detective is basically useless because the retrieval of information, the evidence gathering, it's being bottlenecked by the manager who has no idea what they're doing.
And that, in a nutshell, is the state of artificial intelligence right now. We are living in this really strange era. We have these massive reasoning models, GPT-5, the new Gemini iterations, that are effectively digital geniuses. They can plan, they can code, they can reason, but the plumbing, the way they actually get information, it's still stuck in 2024.
It really is the paradox of the modern AI stack, isn't it? We've spent billions and billions of dollars scaling the brain, the large language model, but we are still feeding that brain with a spoon that we built 3 years ago. It's kind of absurd when you think about it.
Which brings us to the deep dive for today. We're looking at a paper that I think finally cuts the blindfold off the detective. It's titled ARAG, Scaling Agentic Retrieval Augmented Generation via Hierarchical Retrieval Interfaces. It's coming out of the University of Science and Technology of China and Metastone Tech.
And this paper is making some serious waves. It's making waves because it challenges the fundamental assumption of how ARAG, that's Retrieval Augmented Generation, should even work.
The key word that grabbed me wasn't retrieval, it was agentic. We throw that word around a lot, Everything is an agent now. If my toaster burns my bread, it's an agentic failure.
Right, it's a buzzword.
It is. But in this paper, they are defining it very, very specifically.
They are, and it's a crucial distinction. I mean, up until now, most RAG systems have been passive. The AI just sits there, it waits for data to be fed to it, and then it talks. ARAG proposes a system where the AI has autonomy.
Okay, so autonomy. What does that actually mean in this context?
It's the difference between a student who memorizes a textbook because they were told to, and a grad student who knows how to walk into a library, use the catalog, get lost in the stacks, and find an answer to a question that isn't even in the syllabus.
That is the mission for this hour. We are going to unpack the methodology of ARAC-Me. I don't just want to talk about the results, although, spoiler alert, they beat the pants off existing systems. I want to look under the hood. How do you actually build a system that lets an AI decide for itself what to read? Because from an engineering standpoint, that sounds like a nightmare of infinite loops and, hallucinated searches.
Oh, it is. It's a very dangerous architectural choice if you don't have guardrails.
Oh, yeah.
So we need to talk about 3 specific things today: the hierarchy of information they build, the toolkit they give the agent, and this really clever mechanism they call the context tracker.
Okay, but before we get to the solution, I want to spend some real time on the problem, because I think a lot of people listening might be thinking, wait, my RGAC system works fine. Does it? Or do you just think it works fine because you haven't seen it fail yet?
That's the most dangerous thing about RAG. It fails silently. You ask a question, you get a confident-sounding wrong answer, and you don't know that the system just missed the one document it needed.
Let's dissect the old way then. The paper calls it naive RAG, and this is, for all intents and purposes, the industry standard. Walk us through the mechanics of a naive RAG query. Let's use a concrete example. Say I ask the AI, where was Alex's wife on March 4th?
Okay, good one. A simple multi-hop question. In a naive RAG system, the process is completely linear and what they call single shot. Step 1. The user types the prompt. That's it.
Okay.
Step 2. The system takes that exact text, where was Alex's wife, and converts it into an embedding, a vector.
Pause there for a second. Vector. We say it all the time, but practically speaking, what is the system actually doing? What's it looking for?
It's looking for mathematical similarity. It turns your question into a long string of numbers. Think of them as coordinates in a massive multi-dimensional space. Then it looks at its database, its library, which is also just a pile of vectors, and it tries to find the documents that are closest to your question in that space.
So it's looking for vibes. It's not looking for words. It's looking for the mathematical representation of the idea.
Essentially, yes. It's looking for semantic overlap. So it grabs the top, say, 5 documents that share the most mathematical DNA with your question. It then glues those 5 documents together into one big block of text, shoves that block into the prompt, and tells the LLM, answer the question using only this context.
And that's it. One swing of the bat.
One swing. And here is precisely why it fails for your question about Alex's wife. The vector search is likely going to find documents that contain the words Alex and March 4th.
Right, that makes sense.
But the answer to where was Alex's wife relies on a critical piece of information that isn't in the question, the wife's name.
Oh.
If the documents about Alex don't explicitly say Alex's wife Betty was in Paris, but instead a separate document says Betty was in Paris, the vector search might miss the Betty document entirely. Because the vector for Betty doesn't look mathematically similar to the vector for Alex's wife unless the model has been specifically trained to know that relationship.
So the system retrieves 5 documents all about Alex. Maybe his work history, his trip to London. None of them happen to mention where his wife was. The system hands those to the AI. The AI looks at them and says, what?
It says, I cannot answer this based on the provided context, or worse, it hallucinates. It might see Alex and London and say Alex's wife was in London because that's the only location it has to work with.
Exactly. The AI is the genius detective, remember. It could figure this out. It could form a sub-question like, hey, this is useless. First, I need to find out who the wife is. But in naive RAG, it doesn't have a mouth. It can't ask for more data. It's a passive receiver.
It's completely passive. It has no agency.
It's strictly input-output. There is no loop. There's no feedback.
Correct. And that is why we call it naive. It makes this huge assumption that the user's question contains all the necessary semantic keys to unlock the answer in one shot. For any complex multi-hop question, that is almost never true.
Okay, so engineers realized this pretty quickly. This was the big headache of 2024. So then we move to what the paper calls workflow RAG, or sometimes you hear agentic workflows. This is where we started drawing flowcharts.
Right. We tried to hard-code the detective's intuition into the system.
If user asks X, do step 1, then do step 2. If step 1 fails, do step 1B. It's logical, it seems like the next step. So why does the paper argue this is broken too?
Because it's brittle. It's so brittle. Think of it like a customer service script. You know when you call an airline and the automated voice forces you through a menu? Press 1 for reservations, press 2 for baggage.
And I'm just shouting representative
Yeah.
at the phone over and over because my problem doesn't fit into one of their neat little boxes.
Exactly. Workflow RAG is a predetermined decision tree. The engineer decides beforehand how the AI should research a problem. They might create a workflow that says, step 1, always search for the subject's name. Step 2, then search for the date. But what if the question doesn't have a date? What if the question is super simple and doesn't need a multi-step search at all?
The workflow runs anyway.
It runs anyway, it burns tokens, it wastes time and money. Or conversely, if the problem is really, really hard and needs 10 steps to solve, but the engineer's workflow only allows for 3, the AI just hits a wall and stops. It lacks adaptability. It can't adjust to the difficulty of the problem in front of it.
So naive RAG is too passive. It's a bystander. Workflow RAG is too rigid. It's being micromanaged by a human engineer.
And that brings us to the core problem definition that Du and the team at USCC are trying to solve. They want to leverage the reasoning capability of the model to manage the retrieval process.
They want the detective to be able to say, wait, this evidence is garbage. I'm going back to the crime scene myself.
They want to close the loop. They want the output of the reading step to influence the input of the next searching step. It's about creating a true feedback mechanism.
To help visualize how they do this, the paper leans heavily on a library metaphor. And I actually want to push on this analogy a bit because I think it explains the ARAG architecture better than any schematic diagram ever could.
It's the best way to understand the hierarchy part of the title. It's all about levels of information.
So in the old world in naive RAG, I walk into the library and a librarian just throws a random stack of books at my head and says, good luck.
And you're not allowed to get up from your chair. You can only read what they threw at you.
Right. Now, in the ARAG world, I walk into the library, I am the agent. The library is massive, millions and millions of documents. How does this methodology change the way I interact with the books?
Well, first, and this is the most important insight, it recognizes that you don't interact with information at just one level. This is the concept of granularity. When you go to a real library to find something, you don't start by opening a random book to page 45 and just start reading.
No, of course not. I start at the computer catalog.
You start with high-level metadata. You look for a title or an author or a category. That is what we'd call coarse-grained information. It's a summary.
Then I find the right aisle, the right shelf. I look at the spines of the books.
That's medium-grained. You're narrowing it down.
Then I pull a book that looks promising. I open it. I scan the table of contents, maybe the index in the back. That's fine-grained. And then, only then, after all that browsing, do I actually commit to writing the text on a page.
That distinction, the difference between finding and reading, is what ARAG operationalizes. In naive RAG, finding and reading are the same thing. You do a search, you get the full text. That's it. In ARAG, they are completely decoupled.
This is the hierarchical interface they talk about. So the AI isn't forced to consume the entire content immediately. It has layers it can peel back.
It has layers of visibility. It can peek at the shelves without having to pull down every single book. And this is crucial for efficiency. If an AI had to read every document just to find out if it was relevant, the cost would be astronomical. It needs a way to browse efficiently.
Okay, so let's build this library. The paper describes an offline phase. This is basically all the setup work you do before you let the agent loose. And they structure the data in a very specific three-tiered way that enables this browsing.
This is the indexing construction part. And there is a nuance here that is really easy to miss, but I really think it's the secret sauce of the whole system.
Walk us through it. Step one is chunking, which is pretty standard practice.
Yes. You take your massive PDF or your text file and you chop it up into smaller pieces. They use a chunk size of about 1,000 tokens.
Which is what, in plain English? 2-3 pages of text?
Roughly, yeah. A substantial amount of text that can hold a complete thought. Now, usually in standard RAG, you would take that 1,000 token chunk, you'd turn it into a single vector, and you'd save it in your database.
Right, you index the chunk itself.
But the authors argue that a 1,000 token chunk is too blurry for a vector. If a chunk of text talks about apples and then oranges and then a little bit of nuclear physics, the final vector for that chunk is going to be this weird mathematical average of all three concepts. It loses precision.
It's the muddy color problem, right? If you mix all the paints together in a bucket, you just get brown.
Exactly. So step 2 in their setup is where they deviate from the norm. They keep the 1,000 token chunk as the reading unit. That's the thing the AI will eventually read. But for the index, the thing the AI searches, they break that chunk down into individual sentences.
Wait, so they index every single sentence separately?
They create embeddings for the sentences. They turn each sentence into its own vector.
That sounds huge. Isn't that exploding the size of your index? It must be way more expensive to store.
It is larger, yes. There's no getting around that. But think about the precision you gain. Now, if I search for the core principles of nuclear physics, I'm not getting a muddy match on a 3-page document. I'm matching the exact sentence where the author discusses it.
But, and here's the clever part, I'm guessing. When the AI finds that perfect sentence, the system doesn't just hand back that one sentence, does it?
No, that would be incredibly dangerous. A sentence taken out of context is how you get misinformation. If the AI finds the perfect sentence, the system maps it back to its parent chunk and says, here is the book that this sentence came from. Read this whole section for context.
So you search for the needle, but you retrieve the haystack.
Or at least the bale of hay immediately around the needle. You get the full local context. This solves that lost in the middle problem, where an important detail gets missed by the AI because it's buried in the middle of a long document. By indexing at the sentence level, nothing gets buried.
Okay, so we have the sentence vectors for the semantic layer, the meaning layer. But there is another layer, the keyword layer. And I was surprised by this part of the paper because usually building a keyword index is step one. You build this massive inverted index, basically a dictionary of every single word in every single document.
Right, that's Elasticsearch 101, standard stuff.
But the authors say, no thanks. They don't build a global keyword index at all. Why? Why would they skip that?
They call it a lazy design choice. And in computer science, lazy is often a compliment. It means just in time. Building a global index of every word takes a lot of memory and a lot of time up front. And frankly, 90% of those words will never, ever be searched for. It's wasteful.
So how do they do keyword searching if they don't have an index? You can't just search nothing.
They utilize the structure they already have. When the agent asks for a keyword search, the system scans the raw text of the relevant chunks on the fly. It's a trade-off. They save massive amounts of setup time and storage at the cost of a tiny bit of extra compute during the search itself.
But isn't scanning on the fly really slow?
Not when you have modern hardware and you aren't scanning the entire internet. Remember, this is usually being used on a company's internal documents or a specific data set. Scanning a few thousand text chunks for a string match takes milliseconds. It's fast enough.
So the library's built. We have our chunks, which are the books. We have our sentence vectors, which is like the librarian's deep knowledge of the content. And we have our on-the-fly keyword capability, which is like the catalog. Now, we need to talk about the librarian, or maybe the library card we give to the AI.
The toolkit.
Yes, the toolkit. And the paper is very disciplined here. They don't give the AI 100 different tools to play with. They give it exactly 3.
And that's a good thing. Constraint breeds creativity. If you give a model too many tools, it gets confused. It's called the paradox of choice.
Tool number 1, keyword search. This seems so old school. Why do we still need keyword search in 2026? Shouldn't the AI just understand everything semantically by now?
I love this question because it highlights a major misconception about AI. Vectors are fuzzy. They're probabilistic. If I search for the name du, the author of this paper, using a vector, I might get do or to.
Vectors are bad at spelling.
They are terrible at it. And they're even worse at exact IDs. If you are looking for invoice number 99482, a vector search is completely useless. It will give you invoice number 99483 because the numbers are mathematically close. For specific entities, you need exact string matching.
So keyword search is the scalpel. It's for precision.
It is the scalpel, and the authors added this little heuristic here that I found delightful. When the AI does a keyword search, they don't just count the words, they weight them by length.
Explain that. Why does length matter?
Well, if the AI searches for the phrase the bank, the word the appears in every document. It's just noise. The word bank is pretty common. But if the AI searches for Citibank, that is a longer, more specific token. The system assumes that matching a long word is more valuable and more indicative of relevance than matching a short, common word.
It's a simple heuristic for information density. The longer the word, the more information it likely contains.
Exactly. It's simple, but it prevents the system from returning garbage just because a document has a lot of these and ands.
Okay, so that's the scalpel. Tool number 2, semantic search. This is the vibe check.
This is for when the AI doesn't know the specific keyword. The classic example is, what are the environmental impacts of the HIERARCH methodology? You don't know what specific words the author used to describe those impacts, so you search for the concept.
And this search hits that sentence index we talked about building earlier.
Correct. And it returns snippets of the most relevant sentences.
And that's a key point. Both of these tools, keyword and semantic, they only return snippets, right? They don't give you the whole document.
That is absolutely critical. They are browsing tools. They're like reading the back of the book or the table of contents. They help the AI decide if it wants to commit to reading.
Which leads to the agent's most important button. Tool number 3, chunk read.
The commitment tool.
Yeah.
This is the main event.
This is the moment the AI says, okay, I have browsed enough. I've seen the snippets. I think the answer is in chunk ID 45. Give me the whole thing.
And this is the only time the AI incurs the real cost of reading the full context. It's the expensive action. So it should only be used when the AI has a high degree of confidence.
The paper also mentions it can read adjacent chunks. Why is that important? Why not just read the one it found?
It's to handle context bleeding. Imagine the search snippet shows the very beginning of a sentence. The secret solution to the problem is, and then the chunk ends.
The cliffhanger.
The ultimate cliffhanger. The AI needs to be able to say, turn the page. So it can request chunk 45 and also chunk 46. It allows for linear reading, which is something that most disjointed RA systems really struggle with.
Now, before we see this in action, we have to talk about the context tracker. Because up until now, this sounds like a system that could easily go off the rails. What stops the AI from just searching for apple, reading chunk 5, then searching for apple again, finding chunk 5 again, and reading it again forever?
The infinite loop of stupidity. The agent just gets stuck.
Yes. The Groundhog Day bug.
This is a huge, huge problem in autonomous agents. They forget what they've done. So the authors built a stateful memory directly into the interface. They call it the context tracker.
It's basically a do not call list for data chunks.
That's a perfect way to put it. It keeps a running log of every single chunk ID the AI has successfully called chunk read on. So if the AI tries to call chunk read on ID 45 a second time, the system intervenes. It doesn't even run the tool. It returns a system error message that says, you have already read this chunk. The information is in your context.
I love that. It's like a parent telling a kid, you already looked in the pantry, the cookies aren't there, look somewhere else. It's a gentle nudge.
It forces exploration. By blocking the repetitive known path, the AI is mathematically forced to try a different query or a different tool. It drives the agent toward finding new information, not just confirming old information.
It turns a bug, which is repetition, into a feature, which is forced diversification of strategy.
It's a brilliant, lightweight way to handle state without needing a massive, complicated memory bank for the agent. It's just a simple list.
Okay, we've built the library, we've trained the librarian, we've given the detective their 3 tools and their do not read list. Now, let's watch the detective work. This is section 5 of the methodology, the agent loop.
This is where it all comes together. They use a standard framework called REACT, which stands for reasoning and acting. It's a cyclical process of evaluation, tool selection, observation, and then more reasoning.
I want to go back to our original example from the beginning. Where was Alex's wife on March 4th? Let's simulate the AI's inner monologue step by step using the ARReg system.
Okay, let's roleplay the AI. I'll be the model's thought process.
Perfect. So, step 1, evaluation. The prompt comes in.
The AI thinks, okay, I have a query about a person named Alex, his wife, and a specific date, March 4th. I do not know who the wife is. I do not know where she was. I cannot answer this yet. I need to gather information.
So it acknowledges its own ignorance. This is already a huge improvement over naive ARReg, which would just make a guess. So step 2, tool selection. What does it do?
The AI thinks. The first logical hurdle is to identify the wife. The name Alex is a specific entity. I should use the keyword search tool for the terms Alex and wife to find text where they appear together.
It chooses the precision tool, the scalpel. Okay, step 3, observation. The system runs that keyword search. What comes back?
The system returns a list of snippets. Let's say it returns a snippet from chunk 15 that says, Betty has been married to Alex for 10 years. And maybe another snippet from chunk 99 that says, Alex and his wife went to dinner last Tuesday.
Okay, interesting. Now, step 4, reasoning. The AI analyzes these snippets.
The AI thinks, okay, I have a probable name. Chunk 15 explicitly states Betty is married to Alex. She is the wife. Chunk 99 is vague and doesn't add new information. So my goal has now shifted. I no longer care about the phrase Alex's wife. I care about the name Betty. I need to find where Betty was on March 4th.
This is the pivot. This is the multi-hop moment that breaks the old systems.
Exactly. The plan updates dynamically based on new evidence. So now we go to step 5, iteration. The AI selects a tool again. But what tool does it use this time?
Well, you could use keywords again, right?
Yeah.
Betty and March 4th.
It could. But a smart agent might reason differently. It might think, I don't know exactly how the text will describe her location. It might say travel or flight or hotel or conference. A keyword search is too narrow. I should use semantic search to cast a wider net for concepts related to her location.
So it writes a new query, something like, Betty travel plans March.
Exactly. Note that it is searching for Betty now, not Alex's wife. This is the critical step that naive ARRAG misses entirely.
The system runs the semantic search. It returns a snippet from, say, chunk 35. Betty finalized her itinerary for the spring trip to Asia.
The AI thinks, okay, this looks very promising. Itinerary and trip are strong signals, but this is just a snippet. I can't trust it to have the full details. I need more context.
Which leads to step 6, reading. The AI finally decides to commit.
It calls chunk read on chunk ID 35.
And the system delivers the full 1,000 token chunk. What does it say?
It downloads the full text, and it reads, Betty finalized her itinerary for the spring trip. She will depart for Beijing on March 2nd and will remain there to attend a tech conference until March 10th.
Bingo. March 4th falls squarely between March 2nd and March 10th.
The detective has the smoking gun. The evidence has been found and verified.
So finally, step 7, answer. The AI breaks the loop.
It now has all the pieces. It synthesizes the final response. On March 4th, Alex's wife, Betty, was in Beijing attending a conference. And crucially, it can cite chunk 15 and chunk 35 as its sources.
It feels incredibly human. It's not just matching patterns anymore. It's a genuine investigation.
And it satisfies the paper's own definition of true agentic autonomy. They define 3 pillars for this: autonomous strategy, iterative execution, and interleaved tool use.
Okay, break those down for us. Autonomous strategy.
That means I, the AI, decide the plan. No human wrote a flowchart saying first search name, then search date. The AI figured that out based on the logical structure of the problem.
Iterative execution.
That means I can try again. If the first search for Betty had failed, the AI could have gone back and tried a new keyword search for Alex's spouse or Alex's partner. It has retry logic built into its intelligence, not hard-coded by an engineer.
And interleave tool use.
This is a big one. It means I can mix and match my tools. I can do a keyword search, then a chunk read, then a semantic search. I'm not stuck in a rigid search, then read pipeline. I can adapt my tools to the information I'm finding.
It's fluid.
It's organic. It adapts to the difficulty of the question. If the question was easy, it might solve it in one step. If it's as hard as our example, it takes 7. If it's even harder, it could take 20.
But this brings us to a really important reality check. We've painted a very rosy picture so far. But every methodology has assumptions. Every system has a breaking point. Let's look at section 6 of the paper. Assumptions and so what?
Right. The elephant in the room is what I call the competence assumption. ARAG delegates the entire control flow to the model. It says, you drive. That works wonderfully if the driver is sober and has a license. It works if you are using a powerful model like GPT-4o or Claude 3.5 or whatever the 2026 equivalent is.
But if you try to run this with a smaller, dumber open source model?
If the underlying model can't reason well, the whole thing collapses into chaos. A dumb model will get stuck in loops even with the context tracker. It will choose the wrong tools. It will misinterpret the snippets it gets back. Naive RAG is actually safer for dumb models because it holds their hand and forces them down one path. ARAG requires a high IQ threshold to work effectively.
So you can't just run this on a pocket calculator. The quality of the detective is paramount.
It is. The backbone model is the single point of failure for the entire strategy.
There's also a structural assumption about the documents themselves, isn't there? They assume the information is hierarchical.
Yes. They assume that if a keyword or a relevant sentence appears somewhere, the surrounding chunk of text is also relevant. And for well-written articles or books, that's usually true. But imagine a document that is just a list of random, disconnected facts, or a dictionary.
Or a transcript of a chaotic meeting where people are constantly interrupting each other and changing the subject.
Exactly. If the context around the sentence doesn't actually relate to the sentence, then the chunk read action is a complete waste of money and tokens. The methodology implicitly relies on well-structured, coherent documents.
Now, I want to pit this against the other heavyweight champion of 2026, GraphRag. We did a deep dive on knowledge graphs last year. That approach involves building these massive spider webs of entities and relationships. Alex is connected to Betty, Betty's connected to Beijing.
GraphRag is incredibly powerful. It's the structured approach. You pre-compute all the relationships you can find in the text.
But the authors of this paper claim ARAG beats GraphRag on a lot of benchmarks. Why would that be? A perfect graph seems unbeatable.
Because GraphRag is rigid in its own way. The graph is only as good as the extraction algorithm that built it. If the graph builder didn't create a link between Betty and Beijing during the setup phase, the AI can't traverse that path. It doesn't exist.
So if the relationship is stated in an unusual way that the algorithm misses, you're out of luck.
You're out of luck. ARAG doesn't have that problem because it uses the raw text. It goes to the source every time. It doesn't rely on a pre-built and potentially flawed map. It relies on the detective's ability to read the terrain in real time. It's lazy exploration versus eager mapping.
And lazy is cheaper, as we discussed.
Much, much cheaper. Building a knowledge graph for 1 million documents takes a massive amount of GPU hours. The indexing for ARAG is fast. You just embed the sentences, and you're ready to go.
So if you have a messy, constantly changing data set, ARAG might be a better choice. If you have a highly structured, static data set where you can invest in building a perfect graph, maybe GraphRag wins.
That's a fair assessment. But the benchmark results in the paper are pretty telling. They show ARAG winning on almost all multi-hop question-answering tasks. The flexibility of the agent seems to trump the pre-computed structure of the graph in most cases.
There was one final chart in the paper that I want to highlight before we close. It was about test time compute. This really jumped out at me.
This is probably the most exciting theoretical finding of the whole paper, I think.
Explain the correlation they found. It seemed almost too good to be true.
They found a nearly perfect linear relationship between the number of steps they allowed the agent to take and the accuracy of the final answer.
Meaning if I let the AI think longer, it literally gets smarter.
Exactly. In the old paradigm, if you wanted a smarter answer, you needed a bigger model. You had to upgrade from the 70 billion parameter model to the 1 trillion parameter model,
Which costs an absolute fortune both to train and to run.
ARAG suggests a different scaling law. You can keep your smaller, cheaper model, but just give it more time. Give it permission to take 20 search and read steps instead of just 5. Its accuracy will go up predictably.
It's the difference between asking a genius to answer a complex question in 3 seconds versus asking a smart grad student to answer it in 3 hours. The grad student might actually produce a better, more well-researched result because they have the time to be thorough.
Precisely. We are trading compute time for intelligence. And ARX is the framework that facilitates that trade. It allows the model to chew on the problem until it's solved.
That fundamentally changes the economics of AI deployment. It means we don't necessarily need bigger and bigger brains. We just need better research methods for the brains we have.
And a little more patience.
So let's wrap this up. We've unpacked the methodology of ARAG. At its core, it moves us from static pipelines where the human decides the logic to dynamic agents where the AI does.
It gives the AI a library card, which is the hierarchical index. It gives it a set of glasses, which are the search tools, and it gives it the permission to browse, which is the agent loop.
And it solves that fundamental disconnect we started with. The genius detective is no longer blindfolded.
The detective is free to do their job, finally.
I want to leave our listeners with a final thought about where this goes next. We've been talking this whole time about documents, PDFs, text files, but the methodology we just described, that loop of evaluation, tool selection, observation, it's abstract.
It is completely content agnostic. The logic doesn't care what the tools do.
Exactly. So what happens when the library isn't a database of text? What happens when the search tool is an API call to a live stock market feed? Or a tool to search a private database of DNA sequences? Or a tool to view a live camera feed from a security system?
That is the big provocative thought here, isn't it? ARAG describes a generic loop for gathering information. That information can be anything. If you give the same agentic structure tools to sense the physical world, the same reasoning loop applies. The AI could think, I need to know the temperature in this room. I will select the thermometer tool. I will read the value. Observation, it is cold. I will now select the heater on tool.
We aren't just looking at a better search engine for our documents. We are looking at a potential operating system for autonomous agents in any domain.
We are moving toward a world where we don't code the process. We don't tell the robot how to walk step by step. We only code the environment and the tools available, and we let the model figure out the rest.
ARAG is just the first really successful deployment of that philosophy in the text domain. But it won't stay in the text domain for long.
And that is both incredibly exciting and slightly terrifying.
That's technology for you. On that note, thank you for diving deep with us today.
Always a pleasure.
Keep questioning the black box and keep diving deep. We'll see you next time.